Everyone. My name is Yuanhong from University of Nevada. Today I'd like to talk about the magnetospheric emission from the Magnetar crust quakes in fast radio bursts. Okay, so first I'd like to briefly introduce what is FRB. FRBs are basically the highly dispersed. You will first see the high frequency components arrive earlier, and the lower frequency components arrive later. So it's highly dispersed, and it's very short time duration, roughly millisecond time duration, and it's very bright because the brightness temperature is very high in the radio sky. And we know in 2020, there's a SGR can produce FRBs in our galactic. And you can see, based on this, at least we can say there are some magnetars can produce FRBs. And so FRBs are generally divided into two types. One is non-repeaters, which means you only see the burst one time from the same source. So you'll never know whether this is repeated again in the future. And the other one is repeaters, which means you see it many, many times from the same source. Here I'm showing you a very active repeaters detected by FAST. So you can see the time duration is millisecond, which is very short, and it including multiple peaks. So this is like a common features in very active repeaters. Until now, we don't know what is the trigger mechanisms. One possibility is from the magnetic crust quakes. So since the magnetic stress is very large to break the crust, and the twist is there, and it can occur in the deep crust, and it will shake the B field to generate waves. But I want to say the crust is not a completely rigid body because it's just like the jello. And when you have a crust is moving, the B field are frozen in. So the crust is moving and the B field will moving together with the crust. And it will shake the B fields and launch the waves. Okay, if we go into the deep crust, we just consider there's a crust quake, and it will generate the magnetic elastic waves, and the waves will reach to the surface and do some perturbations. Because the hydrostatic pressure is very high, so it will suppress any displacement along the radial direction. So it's basically, you only have horizontal displacements, and it's incompressible. So based on the equation of state, we can know the wave speed of the elastic wave. So you can see in the crust, the speed is roughly equal to the 0.01 speed of light. And you can also calculate the characteristic frequency. It's 10 to 4 or 10 to 5 radian per second. Okay, so when the wave reaches the surface, because we know the electric conductivity is very high, so the V cross B will directly give you what is the induced electric field. So if you consider the displacement is completely perpendicular to the B field, and in this case, you will find out the induced E field is parallel to the KB plane, and you can have Rn waves. So you can calculate the motion equation, and you can obtain the effective mass density and the effective modulus, which are also related to the local B field. But another case is if you have a displacement which have a component parallel to the B field. So in this case, you can have some compressional wave generated in this case, and you can find out the induced E field is perpendicular to the KB plane. And now you have fast mode. So you can see there's a slightly difference between the Rn and the fast is the effective mass density depending on the B. One is depending on the BZ. And this will slightly do some modulation on the shear modulus and influence the transmission. Okay, so one propagation effect in the crust is since the wave is moving, and when the wavelength is comparable to the local scale height, and you will have WKB reflection. The velocity actually including two terms. One is related to the modulus and the mass density, and the other term is related to the B field. So for magnetar with very high B field, the second term will dominate. And near the pole, the theta zero is basically zero because the B field is nearly perpendicular to the surface. So you will see the second term will dominate the transmission coefficient, and you will have this expression. But in other case, in the equator, the theta 0 is nearly 90 degrees. So you will see the first term will dominate, and you will have different scaling on the B field and the cosine theta. Okay, and you see there are just a small fraction energy goes to the magnetosphere due to the very large mismatch between the two impedance of the magnetosphere and the crust. But you will see that there's larger energy will goes into the core. So you can calculate what is the damping time scale. It's roughly 10 milliseconds. So in our simulation, basically we solve this motion equation. We use the incompressible condition. And the first term in the right-hand side describes the elastic restoring force. And the second term describes the Lorentz force because you have B field. And we use the spectral method to solve this equation, and we use the simplified radiation boundary condition. Here I'm showing you three different time points. The first time is, we choose 0.2 milliseconds during the first, the elastic wave crossing time. So you can see the elastic wave still not reach the surface. But after millisecond time scales, it will spread out, but mainly it will radially propagate, touch the surface. And you see it has two different velocities. One is theta direction and the phi direction, and they will produce fast mode and Rn waves. Okay, first we look at the when the quake happening at the pole region, where the B field is completely perpendicular to the surface. So in this case, the velocity is actually symmetry in the phi direction, and basically you only have Rn waves. And you see the green line denote how many energy goes to the core, which is larger than the magnetosphere. And the quake energy damped roughly millisecond time scales, so the orange line decrease. But you see the total energy are conserved, which is black line. And if you look, go to the equator region, where the B field is actually perpendicular and lies on the surface, in this case, you can have both modes, which is Rn, and you can have red line fast mode. So the next question is, what is the connection between the low frequency kilohertz waves to the high frequency gigahertz waves? Before that, I'd like to share some of the common features and constraints from very active repeating FRBs. So the first thing is, we know that for most repeating FRBs, it has very narrow spectrum, which means if you use a Gaussian function to fit the spectrum, the delta nu over nu is roughly from 0.1 to 0.3. If we just consider there's a spherical geometry, at each point it's producing monochromatic photon. In this case, due to the highlighted effect, you will have a naturally spreading, which is 0.58, and this is the first reason we want to go to the magnetosphere. And the second point is, we see most bursts have very high polarization, including very high linear, or it can have very high circular polarization. And we also see some bursts have PA swing, and described by the pulsar's rotating vector model, and some bursts have PA swing, even have PA jumps, which means you need one mechanism can produce both modes, comparable X mode and O mode. And the third thing is, there is one FRB, same as the PA swing one. People use the scintillation to constrain the index and find out the emission size is actually below the light cylinder. So today I want to share with you one possible scenario is the crust quake will give you fast mode. And this fast mode will interact with the charged bunches. So the frequency will be boosted by gamma square to the gigahertz. And we found the emitted power is very comparable to the FRB, and is very efficient at several hundred magnetic radius due to the cross-section. So you only need a small fluctuation on the background to satisfy the luminosity. And we also predict the polarization depending on how you look at the bunch, depending on the viewing angle. And we could have very high linear and circular polarization. Okay, finally, I want to briefly talk about this propagation. Actually, we calculated the optical depth of the scattering, and we found in the open field line region, if the plasma have a bulk motion with relativistic speed, and the KB angle is smaller in the open field line region, and it can escape. And recently, Bing Zhang has a paper talking about the active repeaters can be powered by magnetars in binary systems with triple aligned geometry, which can also help this problem. Okay, so this is my final slide. So I want to say the Magnetar crust quakes can generate elastic waves, go to the magnetosphere, and most energy will go to the core. And both modes can produce thin and fast, depending on the B-field geometry. And one possible scenario connecting the low frequency to high frequency wave is inverse content scattering. Thanks.
Thanks, Yuanhong, for the talk. Questions? So can I ask you one question regarding the fast wave production from the quakes? So you showed that the effect is probably most significant near the equator. But from that plot, it seems like even near the equator, the fast wave is only like 1 order of magnitude smaller than the alpha waves. Mm-hmm. So can you comment on the efficiency of fast wave production from this?
Yeah, so the efficiency is actually, of course, it's depending on the theta, right? And at the equator, it's very smaller because the B field lies on the surface. And so you see the transmission coefficient is very sensitive to the cosine theta. This is the reason why it's smaller. If you choose another theta between the equator and the pole, it's actually larger. So I just choose 2 extreme cases to show the transmission.
I see. So what's the most optimum efficiency of fast wave production?
So in our simulation, we actually have a figure to show at a different location. Yeah, so in our simulation, we actually see, so you can see this 0 is at the pole region, and you only have Rn. And this is the extreme case I show in the equator. So between the 2 points, you can have larger coefficient.
I see. So you are saying that at other angles,
yes,
the fast wave
in this case,
it's
roughly at 20 degrees.
Comparable. Okay. 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 Thanks. So, any other questions? Can I ask you one more? So in the scenario where you have these beams, Compton scattering on the fast waves, so what do you think is needed as the Lorentz factor of the beams, and how do you get those beams?
Okay, so it's depending on the, so it's just, it's like roughly several hundred to boost the kilohertz wave into gigahertz. This is needed. And how to maintain the bunch and accelerate to balance the cooling is depending on the E-parallel. And the E-parallel mechanism, there are some possible. So we didn't look at that into detail in our model.
See. Okay. Any other questions? Okay, if not, let's thank Yuanhong again.